So this is the last topic in chapter 13, and we're going to be talking about an idea called torsion. And so what is torsion? So torsion is a measurement. So it's a measure of how much a curve, right, a curve like R of t, how much it twists out of a plane. And we'll come back to this kind of general definition here in a second. But another way to write this is really just how much the binormal vector is changing. So it's the change in the b vector of that t in b frame that we've talked about. And a way to think about torsion conceptually is like an extension of curvature into 3 dimensions. So curvature is a value, it's also a measure of a curve, and it is really like a 2D concept. So curvature, a way to think about it is how much a curve deviates from being in a line. So that's the way I want to think about curvature when we compare it to torsion. And so a line, so if your curve is a line, it has 0 curvature because it's completely contained in a line, if that makes sense. So if this is our curve R of t, that equals 0 curvature. And then the farther that our curve deviates from being a line, curvature will increase. So this would have a moderate amount of curvature, this even more so, and then we could really get sharp with the turn, and curvature will increase for these curves. So curvature increases as we deviate from being in a line. And then another note about curvature is that curvature is always in the plane formed by t and n, right? That's that osculating plane. Curvature is always, the local curvature is always in the plane made by t and n, and it's a value of how much the curve is turning or deviating from being a straight line. So that's our comparison to curvature. And now torsion is kind of like the 3-dimensional extension of this idea. So it's how much a curve deviates from being contained in a plane. So if our curve, R of t, lies in a plane across this entire domain, then the entire curve has 0 torsion. So it's how much a curve is trying to jump out of a plane. So if I were to just draw an example here, let me just give an example plane. This might be the xy plane. If this is our curve R of t, and it goes that direction, then because the entire curve lives in a plane, it's not wanting to deviate from being in a plane. So this, in this example, R of t would have 0 torsion. Just like a curve that doesn't stray from being in a straight line has zero curvature. This kind of analogy, or another way of thinking about it as the change in the b vector, holds true for this example as well. So if I were to just plot some example unit vectors on this curve, let me pick the color yellow. So I'll just draw it out here so I can move it around. So these are not going to be representative of the actual t and n vectors, but the b vector will be correct. You'll see here in a second. So these are like my 3 unit vectors like that. If I take them and put them here on the curve, then as I move around, t and n are going to be changing, right? They'll kind of go like this. See, this is where the representation starts to break down. But imagine that the t and n vectors are changing to be in the correct directions. The t and n vectors will still always be in this plane, and the b vector never changes. The b vector is always going to be normal to this plane that t and n are in. And so across the entire curve, if I were to just sketch the b vector, then the b vector would always be pointing straight up in the k direction, right? And even though the vector is changing locations, it's still the same vector. A vector doesn't have a point in space that it lives. It's just a direction of magnitude. And so the b vector would not change. And so there would be zero torsion across this curve. Let me put that right there. And now let me draw another curve, another example curve. Let's go back to like our helix. So if that's r of t, then there is no curve, or excuse me, there's no plane that you could fit this entire curve into, right? The t and n vectors will never be always in the same plane. T and n are always going to be creating new planes as you travel along r of t. And so that would mean that this curve does have some amount of torsion. So in this curve, torsion would exist. Because r of t can't be fit into a plane anywhere, right? So it's always not able to be contained in a plane. And if we were to make this even more extreme, just like we did with curvature, then we could have a curve that deviates from being in a plane even more extremely, right? Something like that would be even higher torsion. So this would be even higher torsion. Right, if I were to draw an example b vector on here, the b vector might be pointing in that direction. And as we traverse along this curve, it's going to extremely change, right? Of course, its length doesn't change. It's always a unit vector. But as we go along this curve, it's always changing direction, right? At every given point, there's always some change in the direction of b. So even higher torsion would exist in this curve than does this curve, and even more so than this curve where there's zero torsion. So the symbol we usually give to torsion is the Greek letter tau. So capital tau, which is Greek for t, for torsion. And the derivation of this formula is beyond the scope of this class, so I'm just going to give it to you. And you can just plug in the values to get torsion at any given point on the curve. And the formula is the determinant of this 3x3 matrix, which has x, y, and z dot dot dot, x double dot, y double dot, z double dot, and x triple dot, y and z triple dot. So the determinant of that matrix divided by the magnitude of the velocity vector crossed with the acceleration vector squared. And these dot derivatives, or this dot notation, so the dot notation, which we give as like x dot or x double dot, for example, that just means like the first derivative or the second derivative. So x dot is equal to like the first derivative of x with respect to t. X double dot is the same thing as x double prime, which would be like d squared x over d t squared. So that's just a condensed derivative notation. And right, these x, y, and z components are the x, y, and z components of your curve. So if your curve is like something I plus something j plus something k, that would be your x function, would be the x's in that determinant. Then you'd have the y function and the z function. So these are the functions you use in that formula, the components of your curve R of t. And then, yeah, remember, it's also divided by the magnitude of v crossed with a squared. So that's the formula we use for torsion. Luckily, you don't often have to compute torsion. This is more of like a conceptual section, and that's kind of how I want to approach it. Okay, let's take a look at two quick examples. So this example one was actually a quiz question I had when I took this course back in 2016. It was given as a 5-minute quiz. So this is a 5-minute quiz question, no calculators allowed. And so it asks us to find the torsion of the following curve at t equals 4, and then we were supposed to give a simplified exact answer. So you couldn't put cosine of whatever or just like the square root and leave it unsimplified. And so we had 5 minutes to do this, and the curve we were given was something like r of t equals the natural log of the cosine of 2t in the I direction plus the square root of 2t plus 4 divided by e to the 2t in the k direction. And so a lot of students in the class I saw as I looked around the classroom as we all, looked at this problem in horror, many students just gave up and turned in an empty quiz or a blank quiz. And there was actually no need to compute the first, second, and third derivatives of all those components, take its derivative, divide by that term in the bottom. There's actually an intuition that you can apply here to make it really easy. So the intuition for this problem is that we know that the idea behind torsion is the tendency for a curve to deviate from being in a plane. And this curve here actually only has two components. So r of t only has two components. Which are the I and k. And so I know that this entire curve, no matter what it looks like, lives in the xz plane. So if I were to just draw an example axis here, because there's only x and z vectors that you can possibly get out of that curve, then you know r of t has to lie in that plane. So we know that the curve, whatever it looks like, is in that plane. And so that's the intuition behind this question. And so because the entire curve is contained in a plane, it only has two components, then we can say definitively, without doing any calculations, that we know that torsion is equal to 0 at every given value of t. So that would include at t equals 4. So that's the answer to this question. You really only needed a couple seconds if you knew the conceptual meaning of what torsion was. And I know in both this example and the example up here, we drew curves lying in like the coordinate planes, like the xy plane or the xz plane. But even if the curve had three components, it could still possibly live in a plane, right? Just for an example down here, a curve with three components can live in a plane. Right, your plane just wouldn't be one of the coordinate planes. So you could have a coordinate system that looks like this. And if your R of t happened to look like that, then there would actually be no way to tell if there was torsion or not. You'd actually have to compute it unless you were able to find the equation of this plane that contained the curve. So if the entire curve lived in that slanted plane, then you would still be able to say there's no torsion. But unless you were able to somehow identify that it lived in that plane or find the equation of the plane that contained the curve everywhere, you would just have to compute torsion for that curve with three components, and it would still come out to show you that zero torsion existed. So let's look at example 2. These are some more kind of conceptual questions. So for part A, we're asked if a curve R of t, or for a curve R of t, curvature is constant and torsion is 0. So what is the resulting shape? So 0 torsion means it's in a plane. And we have constant curvature. So what does that look like? Well, that, you might take a second to think on your own, but it's actually just going to be a circle. So that is a curve with 0 torsion and constant curvature, right? The curvature is constant at every point. It's always turning at the same amount. Now let's look at part B. Part B is for a curve R of t, curvature is constant and torsion is constant. What is the resulting shape? So now we have constant torsion. So it's always, quote unquote, deviating out of a plane at a constant rate. So what does that shape look like? Well, it kind of looks like we're always coming out of a plane at a constant rate, and curvature is constant, so we're always turning at the same amount. That's actually going to result in our helix shape. So that would be our helix that we've seen so much. So a helix has constant torsion and curvature. So this was more of a conceptual chapter, kind of looking at what the idea behind torsion is. I've taught this course for 3 years, and very few times were students ever asked to actually compute torsion numerically. Usually the questions tend to be more conceptual if they're asked at all. Hopefully you understand torsion better and how it kind of relates to an analogous version of curvature in 3D.